Assalamualaikum. Welcome back. So today I'm going to talk about adsorption. So in electrochemistry, adsorption process occurs due to the interaction of species from solution phase with the electrode surface. So let's say we have the electrode. We have two electrodes. One is anode, another one is cathode. So in this solution contain the species to be oxidized at the anode or to be reduced at the cathode. So also solvent is present in that solution. Okay, beside that also probably the additive also present, and also reactants. Okay, so all this will interact among themselves, either the reactant with the electrode or reactant with the solvents. So the type of interaction involved are covalent bonding, electrostatic interaction, or van der Waals. So there are a few factors that can influence the adsorption process. One is the electrode material, the type of material used as the electrode, the potential applied to the system, the solution composition, and also the structure and concentration of adsorbate. So in this case, adsorbate is the reactants. For example, ferrum 2 or ferrum 3. So there are two competition for adsorption. One between all species in solution for the limited number of sites on the electrode surface. So you imagine, so this is the, for example, the cathode surface. So in this solution, okay, cathode, there are a lot of negative charge present at the surface. So in this solution contains solvent, okay, will compete with the reactants, also will compete with other such as additive. So towards this, the surface of electrode. So solvent will try to adsorb on the electrode. Reactant also would like to adsorb, as well as additive also like to adsorb on the, they are competing to each other to the limited side of the electrode surface. This is first competition. The second competition is between the electrode versus the solution. This is the solution. They are compete for this, for example, the target species. So ferrum, for example, this is ferrum 2. It is going to oxidize to form ferrum 3. But ferrum 2 will interact with solution, and also they also like to absorb on the cathode surface. So the competition between the electrode versus the solution for this ion. This is the second competition. So why do we like on the adsorption? Because in electrocatalysts, the researchers like to produce material that have good, which is catalytic material to produce something. So also the new reaction involving surface chemical reaction, and also the inhibition of reaction. So when the chemical or the species absorb on the electrode surface, so if the electrode the product is can inhibit further reaction of the electrode, so we call it inhibitor. So let's look at the example for this adsorption process in the electrocatalyst. For example, hydrogen evolution reaction. So in hydrogen evolution reaction involve the reduction of hydrogen ion to form hydrogen gas. It looks very simple, a straightforward reaction, but actually is a multi-step process. Okay, so there are some possible steps involved in the hydrogen reduction reaction or the hydrogen evolution reaction. For example, in this case, the hydrogen reaction on zinc surface. The electrode is zinc, so in the solution contain hydrogen ion. So there are some possible steps in the production of hydrogen gas. First, the species hydrogen ion must be adsorbed or attached to the zinc surface, so before the reaction can proceed. Okay, so the hydrogen ion in bulk solution will move towards the zinc surface. For example, here, so this is zinc, so this is cathode, so cathode is negatively charged surface. So in bulk solution contain hydrogen ion, so it will move toward this surface through mass transport process. So then it adsorb on the surface, so it will take one electron, this is electron transfer, to produce hydrogen atom or radical. So another hydrogen will also move to the surface, then take another one electron to form another hydrogen radical. So this will form a bonding, so to produce hydrogen bubble or hydrogen gas. So this is still adsorbed at the surface, then slowly it will diffuse to the bulk or in the atmosphere. So this is the 4 possible steps involving the production of hydrogen gas from hydrogen ion. So it adsorbed, then followed with the electron transfer, then 2 hydrogen atom or radical will combine to form hydrogen gas, then hydrogen diffuse away from the metal surface. So the rate of hydrogen evolution reaction will be determined or controlled by the slowest step among all the possible steps. Okay, there are 4, in this case 4 possible steps. So let's say number 2 is the slowest step. So the rate of hydrogen evolution reaction will be determined or controlled by the second step, because second step is the slowest step. Okay, this is like a group assignment. So all, let's say 4 person in this group, so all must cross the finish line in order to be the winner. So if one is missing or fail to reach the final line, finish line, so it cannot be counted. So it must 4 person must cross the finish line in order to complete the assignment. So similar to this case example, the hydrogen evolution involve 4 possible steps. So all must be involved in that reaction in order to produce hydrogen bubble. If one is missing, there is no hydrogen bubble will be formed. Next topic, last topic in this chapter, chapter 1, is about overpotential. So this is the symbol of overpotential, neo. So overpotential, also known as overvoltage, is an electrochemical term which refers to the potential difference between half reaction thermodynamically determined reduction potential and the potential at which the redox event is experimentally observed. So this is the simplified term for this overpotential, which the value of potential experimentally determined will deduct the theoretical cell voltage in order to get the overpotential for that cell or system. Okay, so overpotential, okay, can also be defined as an extra potential which must be applied to an electrode to initiate electroation in an electrochemical cell. Okay, so this is the extra voltage required to make an electrochemical reaction occur. Okay, in electrolytic cell, the overpotential requires more energy than the expected cell voltage. But for galvanic cell, overpotential means that less energy is recovered or generated by the galvanic cell. So both cases, the more energy required or less energy recovered due to the missing of energy in terms of heat loss. So look at this table. Okay, so these all are the value, overpotential values for hydrogen evolution on different material. For example, hydrogen evolution, oxygen evolution, and the formation of chlorine gas on different metals. Okay, first is platinum. So for example, hydrogen evolution reaction, the theoretical value for this hydrogen evolution, if you look at the standard electrode potential table series, so the value is 0 volt. So when you use platinized electrode as the cathode, so an extra 0.07 is required for the hydrogen ion to reduce to form hydrogen gas. Okay, so but for oxygen, let's say we have this potential. So this is current, right? This is current axis, is in ampere. So on solid platinum, this is 0 volt. So hydrogen will immediately form. Okay, 2H plus will produce H2. So you can see bubble form at the cathode. This is negative potential. This is positive direction potential. Okay, so this is positive current. This is negative current. So this is hydrogen evolution, HER, the formation of hydrogen. So on the positive direction, so when the current increase, this is current increase. So the limit on the substrate of material is the OER, the evolution of oxygen. Okay, so for hydrogen oxygen evolution on the standard material or on platinum, so this is the half cell reaction. So the value is positive 1.23 volt. So here 1.23 volt. But on platinized surface, more voltage is required to make it happen. So you have to add another 0.77. It will go to 2 volt in order to see the increase of current on platinized surface. Okay, so if you compare all the material for oxygen evolution, so on gold, it requires the highest extra voltage for oxygen to be evolved. If you compare the hydrogen evolution on platinized with the mercury, so on mercury, the hydrogen evolution will occur at more negative potential. Okay, so for standard hydrogen evolution, this process will occur at 0. But on mercury, so this process is more negative, negative 0.85 volt extra. It's 0.5 volt. This the difference between the theoretical, this is theoretical, and this the new current, the increase of current for reduction. So this one experimentally determined, and this is theoretically calculated. So this difference, we call it overpotential. So it means that on mercury, the evolution of hydrogen is very, very slow as compared to on platinum. Okay, I hope you will understand what is the meaning of overpotential. So on the negative direction potential, so the limit is hydrogen evolution, but on platinum, the hydrogen evolution will occur very fast. But on mercury surface as well as on lead, or on zinc, okay, lead and mercury, okay, the evolution of hydrogen will occur very, very slow. Okay, the difference between the theoretical value from the table with the experimental value, where you can see the current increase, even though it's going downward, but this is negative. It means more. For reduction is negative, for oxidation is positive, upward. It's going upward for oxidation. Okay, oxidation is positive direction, E, positive, and current positive. But for reduction, E, negative direction, and current negative, downward. Negative, it doesn't mean that it's less, more, become less. No, it means that more. This is the sign to show the reduction current. Okay, so for example, for oxygen evolution reaction on standard, this is the process. Water will produce oxygen on platinum surface. This is the standard, 1.23. But on gold, okay, for example, you change this electrode, anode, to gold. So gold, the extra voltage required to produce oxygen, to make oxygen, to form this oxygen, is require more positive potential. So the different, let's say the standard value is 1.23 volt for this oxygen evolution reaction. But if you change the electrode to gold, they require another 1.02 volt extra. So you must add this overpotential, 1.23, add another 1.02. This is the, you will expect at this potential, 2.25 volt, the oxygen start to form on gold surface. I hope you understand about this overpotential. So due to this overpotential phenomenon, so for electrolytic cell, so more energy is required to do the electrolysis. For example, electrolysis of water. So look at this. Okay, one is anode. This is anode because positive charge here. Another one is cathode. This is cathode. Okay, so the reaction at the anode, this is the half cell reaction. So this is the value, standard 1.23 volt. For water reduction to produce hydrogen at cathode, this is 0.83 volt. Okay, you can get it from the table, EMF series or standard reduction potential. So at cathode, the value should be supplied, voltage should be supplied is 0.83. At anode, theoretically 1.23. So the difference here, the voltage required to produce hydrogen and oxygen for electrolysis of water. Alright. Okay. Supposedly, okay, the value is here 1.23 volt at anode plus 0.83. So the requirement for total voltage is 2.06 volt. At least must be supplied in order to start the electrolysis of water. But in the case of overpotential, okay, so the requirement of each electrode at cathode and anode is more, okay, due to overpotential. For example, here, if you use gold electrode, so you need to add 1.02 volt as listed above. So for anode is 2.25 volt because of this overpotential on gold surface. So for this hydrogen, if you use both electrode gold, so the extra 0.09. So you must add 0.09 volt. This is 29. So now more voltage is required at the anode. Okay, at the anode. Now the value, erase first. So this, the new requirement of voltage, this is anode is 2 to 5. Okay, because you add another 1.03 if you use gold electrode. So at cathode, the value, now the value is 0.92. So you just sum up the two half cell reaction. Okay, so 2.25 at anode and at cathode. So the new voltage required to be supplied is higher, 3.17, as compared to the theoretical 2.06. Okay, so you need to supply more energy must be supplied in order to make the electrolysis of water possible. Theoretically 2.06, but experimentally, if you use different electrode material, different condition, you should expect more energy should be supplied, more voltage should be supplied in order to start the electrolysis of water reaction. But for galvanic case or scenario, so less energy. This is opposite. It's a spontaneous reaction, galvanic. So galvanic start from the bottom, chemical reaction, it will produce voltage, generate voltage. Okay, so from chemical energy here, chemical reaction or chemical energy will produce electrical energy. So it's spontaneous reaction. So let's say in this case, copper and zinc is a simple cell, also known as Daniell cell. Okay, between copper, this is copper, and this is zinc. Okay, this is at standard condition. So the value here, E cathode, this is E anode. Right? So the value, if you look at the standard series, this is 0.34 volt. For zinc, negative 0.76 volt. Okay, so what you should expect to get to the voltage generated here is delta E is E cathode 0.34 volt minus 0.76 volt. So you should get produce 1.10 volt for standard condition. But if the overpotential phenomenon occur in the galvanic cell, you should expect less energy, not 1.10 but less than 1.10. Okay, because here at cathode the amount of voltage produced should be lower, as well as this area will be more positive. So delta E produced is no longer 1.1 but less than 1.10 volt. Okay, so I hope you understand that the difference between electrolytic cell and galvanic cell. So for electrolytic cell, more voltage is required to start the reaction. For galvanic, less energy or voltage will be produced when overpotential phenomenon occur in the system. Okay, look at this, the next slide. The overpotential of material for hydrogen evolution reaction and oxygen evolution reaction. So this is the standard hydrogen reaction for acid. Okay, hydrogen plus will reduce to form hydrogen gas. This is hydrogen evolution reaction. So the theoretically, so the value, if you look at the standard, the tab series, so you will find this 0 volt versus saturated hydrogen electrode. So these all are possible steps from hydrogen ion to produce hydrogen gas. Okay, so on platinum black is low overpotential for hydrogen evolution, probably in the range of 0.07 volt. For medium overpotential, such as more platinum, nickel, palladium, rhodium, copper. Okay, so the hydrogen evolution will occur at more negative. So look at this, such as nickel, more negative 0.28 is the medium overpotential. So, but on mercury, lead, stannum, cadmium is very slow, the formation of hydrogen evolution. When it's low, the requirement, for example, this is the theoretical 0 volt, but on mercury, so the value is negative 0.85 volt. Okay, so when then start to form hydrogen gas. Okay, hydrogen gas. But on platinum is 0.07. So this the difference between the theoretical and the experimental. When you change the electrode, for example, from platinum to mercury, it will take high overpotential. Okay, means that high overpotential means that the evolution of hydrogen gas is very, very slow, especially on mercury. Okay, and let's look at this oxygen evolution reaction. So this is the standard half cell reaction for water to oxidize to oxygen. Okay, this is the standard value, 1.23 volt. So if you can see here in this diagram, so on is the purple color is represent gold. Okay, so the most fastest electrode or material is ruthenium. Okay, ruthenium. Okay, the evolution of oxygen will start around 1.43 volt. So the standard is 1.23, only 0.2 volt as overpotential. But on gold, it will occur, oxygen evolution will occur at more than 2 volt, because the overpotential on gold is 1.02 volt. So you must add 1.02 volt to find the new voltage where the oxygen will form on gold, for example. So what are the importance of this phenomenon of potential or overvoltage? Okay, the existence or the presence of this overpotential will explain numerous phenomena. For example, in battery, lead acid battery, during charging, okay, the metal, which is lead, is deposited instead of hydrogen. Okay, so at the cathode, okay, in acid battery, so this is negative. Instead of, because it contains sulfuric acid, so if in acid battery contain platinum as the cathode, the evolution of hydrogen will be vigorously formed. But that's why in acid battery they use lead instead of platinum, because on lead, okay, hydrogen ion will not form hydrogen gas, because on lead, hydrogen evolution is very, very slow. The second importance of overpotential is in the electroanalytical analysis. Okay, for example, in the electrolytic cells for electroanalysis. Okay, so let's say you want to do, okay, let's say this is mercury. Okay, mercury. So let's say this is mercury, Hg. Okay, so the presence of unknown ion of zinc, cadmium, as well as tin. Okay, so for zinc, to reduce, the potential is negative 0.76. Cadmium, not stannum. Okay, all this negative value. For hydrogen is 0 volt. 0 volt. Okay, so logically, if you use platinum as the electrode here, so hydrogen is easier to form hydrogen gas because the reduction, the higher in the series, 0 is higher than this value, so it easily reduced at cathode. But if you change this electrode, instead of using platinum as the electrode, you use mercury. So this process, hydrogen evolution reaction, is very slow to form hydrogen gas on mercury. So it requires extra voltage or overpotential, for example, 1 volt. Okay, but on platinum, 0 volt. But on mercury, it requires extra voltage to produce hydrogen gas, which is 0.81 volt. So due to this phenomenon, overpotential, so you can reduce other elements. Okay, so for example here, negative 0.81, okay, the hydrogen start to form on mercury. But this area, if you use platinum, hydrogen will start at 0. So you cannot do any analysis, for example, to determine unknown in the solution of this if you use platinum, because a lot of bubble, hydrogen bubble, will form on the platinum surface. So you cannot do analysis for the metal cation, other metal cation, okay, zinc, cadmium, stannum, okay. So because the reduction of zinc will occur at negative 0.76 and other metal cation somewhere here, okay. If you use mercury as your electrode, cathode, so zinc can reduce to zinc, cadmium can reduce to cadmium 0, stannum ion can reduce to stannum 0 on mercury. All this can reduce on the mercury surface. So there is no interruption or the from the hydrogen evolution process. That is good about overpotential of different material. The last one, overpotential also plays an important role in the industrial production of chlorine, sodium hydroxide. Okay, this is the chloralkali industry. Okay, using brine, sodium chloride solution. Okay, so if you still remember about the chapter 1A about electrolysis, chloralkali industry. So there are two ways in producing chlorine instead of what you call that, oxygen. Okay, so if you still remember, okay, so this is anode, positive. Okay, so this is the anode is oxidation. Okay, so for water, right, so this value is 1.23 volt. Okay, for chloride to oxidize to chlorine, the value is higher. It's more difficult to produce chlorine. But due to overpotential phenomenon, let's say you use not platinum, okay, other material which is can make oxygen slowly produce at the surface, such as gold form. Okay, so instead of oxygen from water produced at the surface of gold, okay, due to this overpotential, you must add 1.02 in order to produce oxygen if you use gold. So you can produce chlorine. Okay, you can produce chlorine because so chloride in the solution will produce chlorine gas. So because the overpotential phenomenon, so this new potential, the extra potential, okay, will make this potential much higher than the expected one. 1.23. So if oxygen can only be evolved at 2.25 on gold, so chlorine can easily form on gold at 1.36. Another factor which you can produce chlorine is increase this concentration chloride. So the concentration factor or the overpotential can make you produce chlorine. Okay, so this about overpotential. So this problems, there are two questions. So I hope you should answer it first. We will discuss it later. Okay, thank you very much.